So the goal of this talk is to talk a bit about how one could build a high performance computer here in Europe, because at the moment that's not possible, right? Every high performance computer has chips that are made either in Taiwan, that are made in South Korea or the US. There's no high performance computer can actually make all the chips in Europe. And that's a bit sad, right? We have this great technology here, and yeah, we want to change that. At Akhetonics, that's our big goal. We want to build a general purpose, high performance processor where everything is made in Europe. And when I talk about high performance computing or general purpose, I'm not talking about analog computing, right? We heard a lot about, let's call it this analog or this non-conventional way of computing. We use a very advanced technology, but to build classical old school digital computers. And that's a bit something that's often confused because people, when they hear optical computing, they immediately think of the vector matrix multiplication world. That's not what we do. We actually build optical transistors. We actually build optical memory. And these two things allow us to build a regular CPU, and our processors, they execute code. So they execute standard C++ code. They can execute Python code. It doesn't matter. You can run anything on our processor, which includes AI, but is not exclusively for AI. So yeah, a very general purpose device. And we've actually already done that. We've already built an all optical general purpose processor. We have all the components that we need, and it's currently all up to us to create a new computer revolution. And I mean an old school computer revolution in the sense of let's build an all optical version of a GPU, a CPU, but make it here in Europe. And if you look at the current field, right, we of course have to compare ourselves to the existing electronics, to the existing CPUs, GPUs, etc., which are, of course, Intel, NVIDIA, AMD, and all these guys. And they do everything electronically still, right? It's changing. So they have their electronic transistors doing the logic, right? They're doing the arithmetic using digital transistors. And of course, they're moving data around electronically and have electronic memory. Now, the trend is, of course, to replace the interconnects with optics. We've heard about that just now also, right? That interconnects are moving to optics, which is great. We love that. But in the end of the day, if you're not replacing the electronic transistor or the electronic memory, you still have this conversion step. So you're constantly converting either between the interconnects or between the arithmetic, right? If you're doing something like matrix vector multiplication, which is kind of, yeah, to us, it's a bit sad that you lose all the efficiency you have in the photonics by constantly converting back and forth. And that's where we are coming. At Akhetonics, we are doing exactly that. We are replacing the logic and the memory by all optical components. That allows you to always be in the optical domain, and we really mean always. So the data comes in optically through an optical network signal. We process it optically, we store it optically, we do things to it optically, and then send it back out optically through the network interface, meaning there never happens an electronic conversion in our system. And yeah, the reason why we want to do that is, of course, as we heard, the memory bottleneck. Modern GPUs, they're very fast, right? They have huge amounts of compute. All the modern devices have huge amounts of compute, petaops, right? Really nice. But then you see, okay, wait, it only has a terabyte of memory bandwidth. That's a bit strange. And this actually leads to a huge bottleneck that you can actually do 1,000 compute cycles on 1 byte of memory. But what you're going to do with that 1 byte of memory, right? It's a bit sad that we have this huge gap, and it's called arithmetic intensity. So electronic devices simply have an extremely high arithmetic intensity, which is not a good thing. High arithmetic intensity means you have to do much more compute while you wait on memory. The ideal arithmetic intensity is 1 to 1. And that's exactly what optical computing, if you do everything optical, allows you to do. Because now you can do one compute step, fetch memory because you don't have any bandwidth issues, you don't have any memory latency issues, and then you can compute your next step, right? So it's always 1 to 1. We always access one piece of memory doing one compute cycle, which is really nice and allows us to actually increase this performance. Okay, this was a quick rundown of Akhetonics, but what I really want to talk to you guys about today is chips, where they are made, where high performance computing is made, right? We all know that the USA, especially Intel, is making their chips in the USA. Samsung, TSMC also starting to build high performance computers in the US, but we recently heard from, for example, NVIDIA that they're not going to make them in the US. They're still going to make them in Taiwan. So Taiwan, TSMC, huge chunk of all the high performance computers are made there, and that is not about to change with the current approach we have to computing, right? With even if we do something like if we do something like in-memory compute, if we do very advanced matrix vector multiplication in photonics, right? All these have an electronic CPU doing, for example, the activation function or doing some other lifting, which means you can't really build a fully European high performance computer. Now, of course, China is also trying to build their own line for high performance computers at SMIC. And then we have Samsung, who are the only ones who can build these advanced nodes outside of the typical US Taiwan space. Good. So if we want to build a high performance computer based on optical digital computing, how will we actually do that, right? We all know modern NVIDIA devices have billions of transistors. Modern Intel device also billions of transistors. Optics is very large. Our optical transistors, we're not talking nanometers, we're not even talking micrometers. We're already in the almost in the millimeter range, right? So it's a huge device. Also, our optical memory cells, much bigger. The idea is, hey, let's move away from scaling using quantity. Let's move towards scaling using quality. And that's really the whole idea behind photonics, right? We don't scale by adding more transistors. We scale by adding more wavelengths. We scale by adding more time multiplexing and all these things that really allow us to increase performance without increasing the actual size of the chip. And that's really what we're all about. So, but how can we still build a CPU? How can we still build a GPU if we can't even make 1 million of these devices on a chip? And the simple answer is you don't need that many devices. It's a very common misconception that a CPU needs billions of transistors to do modern tasks. That is completely wrong. You can run a modern operating system on a CPU that has just a few hundred, a few thousand transistors. That's absolutely no problem. In the electronic world, it just means you're sacrificing speed. And I want to show you how that works. Because this is a typical electronic CPU. It has 8 cores. It's a Zen processor by AMD. And you will see that a lot of these things we don't actually need. We don't need the memory interfaces, right? We just send the optical signal directly to our optical memory. We don't need 8 cores. I mentioned, right? We scale through quality. We scale through a single core, meaning we can reduce that. So now we're already down to 10% of what we actually need to implement. Okay. Now, I mentioned we have perfect arithmetic intensity, which means we don't need cache. We don't need cache, which is a huge saving on the floor space. Now we're down to a few percent. If we don't need cache, right, and if we don't need any advanced things like floating point for now, right, let's do everything with integers. Then we can also completely remove any optimization features. We remove branch prediction, we remove operand forward, all these things that an electronic processor needs to lessen the blow of the von Neumann bottleneck. We just throw it out of the window because we don't need that. And suddenly you're in the range, hey, wow, okay, we went from billions to now 1 million or a few 100,000 transistors. Can we go further? Sure. We don't need all of those thousands x86 instructions, right? Those are all just optimization instructions. We don't need them. We can reduce it down to a reduced instruction set architecture. And of course, since we don't really need to be in the 64-bit domain, we can go to the 16-bit. We can even do a 32-bit processor. That doesn't matter. It helps us reduce the transistor count down to a few thousand. And that's really where optical digital computing is about. Using a design almost from the 70s, right? And making it run at terahertz, multiplexing it using multiple wavelengths. And then we get very energy efficient system because we only run a few thousand transistors. It doesn't matter if they run in tens of milliwatts, right? That's perfectly fine because we only have a few thousand and the processor is still more efficient. We have extremely low latency because essentially we can't really stop the light, right? So it just flows through our system and we know exactly how fast it flows through our system. And it allows us to build everything in Europe. This really brings forward the European photonics community and allows us to make the first high performance computer fully here in Europe. And we already have the supply chain, right? We have the most advanced packaging houses here in Europe. We have the most advanced photonics integrated circuit manufacturers here in Europe. So let's leverage that and make a high performance computer here, which has a few other benefits. Of course, it's somewhat electronic warfare resistant because it's not electronic, right? You have deterministic computing, meaning it's suited for real-time applications, like for us, right? Our first processors will be in airplanes. So these processors can be used in safety critical environments. You have minimal heat and EM signatures, which is great if you're thinking about any sort of biophotonic applications, etc. And of course, the material platform is as robust as electronics, so we don't have to think about it being super fragile, right? Since everything is integrated, we don't have to deal with lenses. So going back to this picture, let's add another box. Let's add a European box to this picture. And that's really what Akhetonics is all about. And yeah,